So really quick run through of who I am. As Mary said, I have a Ph.D. in soil fertility management. I have a master's in soil chemistry. I have a UC Davis master's in viticulture. My bachelor's degrees are in biology and chemistry. So I'm pretty much a biology / chemistry kind of guy. As a lizard and snakes kind of kid, you know, go out and look over rocks and in forests. And my soils originally started, I was a Peace Corps volunteer in Jamaica as an ag extension agent. I came back to the United States, wanted to get into soils, and then got my PhD at Florida, and they sent me to Cameroon, West Africa for my dissertation research. I worked in that industry for 15 years. I came back to California in –96, went to UC Davis, and then got a job in '97. So I've been at it about 18 years at this point. Mostly Napa, Sonoma, probably 50, 60% Napa, 30 or 40% in Sonoma, and then 10% scattered over the rest of the state. I have been down in the Santa Cruz Mountains several times. I know I've done some work with David Bruce and a few others in this area. In fact, I did the original soils plans on these properties even when they were in escrow many, many years ago. And then I know that there was another soil scientist, a colleague of mine, that did some work here, and then I've come back since a year or two ago to do a little bit more. So I'm not exceptionally familiar with the Santa Cruz Mountain soil types. I know for the most part, what I've seen are mostly sedimentary sandstones and shales. You know, up in Sonoma County is mostly sedimentary sandstones and shales. Most of Napa County actually is volcanics, although there's a mix between the two. So I'm moderately familiar with what you have down here. What I'd like to do to talk about today is somewhat specific because it's one of those subject matters that I feel as though a lot of people think they know somewhat about, but actually don't know much about, and that's the soil physics of the irrigation process and how water moves through soil. And I'm hoping that, you know, when you leave here, you'll be a more capable irrigator of your fields, of your vineyards, especially in those of you that have a fair amount of rock in it, and how to go through the concept of understanding where the water's going, how it's getting there, and then what things you might want to do to increase uniformity or delivery of your system. I'm not going to actually get into irrigation systems, but it'll be looking primarily at the water movement in the soil. If you, let me go to the first slide, because if I can remember how to do this, it's been a while. Let's see, previous page, next page. Oh, come on, machine. No! All right. Oh, there we go. Just slow. That's 2 ahead. There we go. So, like I said, what I want to do is present some basic concepts about the soil physics and the water interface. The presentation is progressive, so it's assuming you probably haven't had much soils in the past, maybe a junior college class in viticulture with 2 weeks of soils, or those of you that have a full viticulture degree, 1 or 2 classes of soils. But I'm going to start relatively basic and then start getting into some more complicated stuff. I hope it's progressive enough that you can follow. If you don't follow, holler. I'll go back a step or 2 and then move forward. If it comes to things that are more personally oriented towards your situation, let's hold those kind of questions until the end. Okay, so, what is soil? Well, it's about 50% mineral, and the other part of it is air or water, one or the other. So when you get out in these fields, even though you think it's solid, it's not. There's a 52% mineral matter, and then the other 48% is made up of organic matter, air, or water. And obviously, the air and the water fluctuates with the season. And right now, it probably has more water. This time in 6 months, it'll probably have more air. Okay, there's many ways of talking about the concept of texture and what the mineral particles are. We have the USDA, the International Soil Science Society. One of these actually is the FAO, UN FAO, and they have various ways of measuring the size of the particles that make up soil. Almost all of them use 2 millimeters. Anything less than 2 millimeters is considered soil. Anything greater than 2 millimeters is considered rock. And it even progresses up from pebbles, gravel, stones, boulders. We're going to deal primarily with the soil today, a little bit on rock. And then there's also some differences you can see here between, you go to here like the IISS is different as far as what's silt and fine silt and fine sand. But for the most part, we have a pretty much agreement as to what's what. Primarily because of the behavior of these particles. And when you start getting above certain sizes, they start to behave, physically, they start to behave a little bit differently. Most of sand is silica dioxide. So it has a lattice structure that makes it have strength of the bonds in all directions are more or less equal, which means that when it chips and breaks, it kind of breaks randomly wherever the force is applied, and consequently it stays somewhat spherical in its nature. Clay, on the other hand, most of the ones that we have in temperate climates are layered silicates. It's kind of like those wafer cookies that kind of have a lattice going through them, those really light airy things that you like when you're a kid, and when you get too old, they're too sugary and you don't want to eat them anymore. That's kind of what a soil clay layer looks like. It's got usually a layer or two of some octahedral and dihydrohedral, and I'm not going to get into all those structures, but it's usually one or two layers sandwiched together, and then there's what's called an interlayer space, and then another either one or two layers stuck together. Because they don't stick together very well, they have a tendency to form two long axes and one thin axis. So you can kind of peel them or chip them, or because they're laminated, they'll separate in the laminated direction, but their edges are a little bit stronger. So they have the dimensions of a book, where it's got one narrow axis and two relatively long axes. And so therefore, clay has a tendency to break into smaller and smaller and smaller pieces, unlike sand. Sand generally does, once it gets down to a certain size, much like when we try to break something, we can only get it broken down even with our fingers to a certain size, and then we just can't get a grip on it to break it anymore, because the internal strength to break that next bit isn't easy based on the dimension of the particle that's left behind. So clays, because they're book-shaped, if you put a little bit of water in between them, they have a tendency to stick together, or glue. And the glue in this situation is usually organic matter. It's the lignins and the, can't remember the other word, that are left over, essentially the soil organic matter, the more or less inert portion of the soil that becomes the soil organic matter that microbes are not really feeding on heavily, and that's why it's soil organic matter, not just compost. But those sort of things stick and hold those clay particles together. So clay forms structure and sticks together better, and it has smaller pore spaces between it than does things like sand. Point it this way. Okay, so once we have this concept of sand, silt, and clay, many of you have seen this kind of thing as the textural triangle. You can see that, for instance, here's the percent by weight of clay. So almost anything greater than 55, or actually anything greater than 40% clay almost is called a clay. Even things that are only 30% clay or 27% clay are called clay loam. So you can see that this triangle up here is really big, because clay, because of the way its behavior, it dominates the behavior of the entire soil mass if it gets to within a certain percentage. Whereas look how much sand there is before you call something just a sand. It's like 10% sand before you call it, well, it's just a sand. Whereas clay, even only 55% or 40% clay is enough to say, oh God, it's so that one particle size is so dominant and so influences the behavior of that mass that we're going to call this a clay, even though it's only 40% clay, and the 20 or 30% of the other constituents, which is always sand or silt. Or because the gravel or the rock has always been taken out. So when you read these, you have to know sand and silt. You need to know two of the variables. In most of the laboratories will measure all three of them, but obviously by subtraction you can figure out the other one. But no matter what soil you have, if it's less than 2%, 2 millimeters in size, and you separate the particles, they're going to fall somewhere on that triangle. Okay, so once we have this concept of the particles, we next get to the aggregation of the particles and how they stick together. And so that's called the soil structure. It's a lot more difficult to explain on something like this. It's easier to see in the field. But we end up things like granular, which is where it's almost spherical in size, and it's about the size of a grape seed, maybe a little bit bigger. It's what we think of when we get into gardening and garden soils that have a fair amount of organic matter. It's usually the surface soil. It frequently is the structure of soils out in native pastures or grasslands. And then next down are the most common are the blockies, the angular blockies and the subangular blockies. These are more or less cubic of various types. Sometimes they'll be trapezoidal or pentagonal. Ones that are somewhat rare
are the polyhedrals. You find this in volcanic ash soils where they don't really go through a shrink swell process, but it looks like flint marks from Native American arrowheads where the facets on the structure are very clearly defined, like a diamond or a cut rock. You have another one up here, platy. Platy is caused, you most frequently see this underneath a drip emitter near the end of the season when you've been dripping water, mostly clean water, clean water, clean water. The clay separates from one another and then it lays down. Because clay is laminated, it has the two dimensions and two long dimensions and one short dimension. It has a tendency to pile down on top of each other and form a laminate. And platy is the result of all those particles forming in a laminated layer. And so frequently you can pick it up, and under an emitter it'll usually only be an eighth or maybe a quarter of an inch thick. Sometimes, depending on natural soil that's been laid down in a lake bed, you can have platy structure that may be 4, 5, 6 inches thick. That was laid down over thousands of years. The other one you get primarily in specialty soils, or very unusual soils, are the prismatic and the columnar. These are usually soils that have very high amounts of the 2-to-1 clay types. The 2-to-1 clays have a tendency to separate. They have that interlayer space, and it separates enough that water can get into that interlayer space, so that when those soils get wet, they have a tendency to swell up. And when they get dry, they have a tendency to shrink. And when they swell up in the winter, there's an intense amount of pressure that's caused by the swelling that forms these usually 8-sided, sometimes 6-sided pillars that can be anywhere from 2 or 3 inches long and an inch in diameter to some that are 5 feet tall and 14 to 18 inches in diameter. And I've been in some up in Napa in the Maxwell clay, which is a serpentinic soil that has a lot of magnesium in it, and the magnesium accentuates this situation where you get in and you get a hole and you have these huge cracks and you can literally just pull these huge pieces with the dimension of a number 2 pencil, except the relative dimensions, but they're really big. They're 18 inches in diameter and 5 feet long. You just literally pull them out in one large piece in a column. Those are not common. In these kind of soils that you have around here, primarily you're looking at granular and the angular and subangular blockies. There's one soil structural type on here that's not here. It's called massive because it's not really considered structure because there's no aggregation of the particles. So it's where the particles are not stuck together in any recognizable pattern, and consequently usually they're massed together with very little amount of airspace between the particles as they've been pushed together. Frequently, these two structures will have massive interiors. There's an exterior structure of this column, but the interior is just massive. So when we start looking at this concept of aggregates going all the way up into structure, the smallest, this is millimeters, millimeters, millimeters. This is the biggest, but you just kind of go with them under a microscope, and you can see that there's things in here like very small soil particles, organic matter, some insects, eggs, or bacteria, all these really, really, really little things, but there's still air in there. There's air between these things. You get up to the next level, which is this little circle here represents this big circle here. You start getting roots, you get hyphae from fungi that are soil-borne. You get more organic matter, but essentially it starts to snowball into these larger and larger particles made up of these smaller and smaller particles to the point where you get to like a 3 millimeter piece, which, like I said, is about the size of a grape seed, in which you have all sorts of things coursing through this thing. You have air pores that are contiguous. That means you can follow them through. It's not just an isolated pore stuck between stuff. There are roots, there are hyphae, there's worms, there's insect legs left over, and it's essentially the soil that is easily recognizable by you even if you just have a hand lens. What I want to go next to is start looking at how some of these things react in relation to water, some of the concepts. We can have soils that are called saturated. That's when all of the pores, all of the air pores that were air are filled with water. You can have what's called field capacity. That's where the soil has been wetted, not necessarily saturated, but it's draining out the bottom, allowing gravity to drain water out the bottom, but there's no evapotranspiration going out the top. So it's essentially the maximum amount of water that a soil will hold in the winter, but allowing for drainage out the bottom. So no saturation, but no evapotranspiration either. So it's essentially about as much water as it can hold. Then you have this concept of the permanent wilting point. That's euphemistic for vine death or plant death because it's permanently wilted. And that's when a soil is so dry that it can't support any plant life. And that's the concept you get when you come back from vacation. You go to your house plants and they're all dead and nobody watered them. And then you feel the soil and it feels dry as a bone, but actually there's probably 2 or 3% hygroscopic water in there that you could, if you put that thing in an oven at 115 or 120 degrees and weighed it before and weighed it after, you'd see that it would still lose weight. That's because there's a small amount of water still in there. So the amount of water between this state is the field capacity at the wettest end, and then the wilting point is the driest state. So everything in between those two states is available for plants to take up. So under a saturated situation, if we just look at the percentage or the amount of soil mass, and this is in grams and milliliters primarily, and it's a little more difficult to comprehend. You don't really need to look at the math on this because soil particles, they have a density of greater than 1. So even though it's here showing 50% more or less of volume, the soil weighs more because it has a higher density than water. But you can see here, when it's saturated, essentially it's all water and or all mineral matter. Once you get to field capacity, there's maybe 20-25% air and another 20-25% water, and then you have your 50% mineral matter. When you get to the wilting point, you only have a very small amount of water left in it. Most of it's air, and then you have this hygroscopic coefficient, which varies depending on how dry you take it. You can put it into various ovens at various temperatures and slowly start to drive this water off. And that can be measured, and some soil physicists do that as part of the research bag. Okay, so with that concept in mind, then we start looking, okay, well, how do these various textures of soil that we have hold water in relation to their water holding capacity of their field capacity? Well, if we look at the field capacity of looking at a soil that is various soils, sand, sandy loam, loam, silt, clay loam, and clay, you can see that sands, even at field capacity, really don't have that much water in them because the pore sizes between the sand is so big that the water doesn't cling very well in there, and it's only clinging by hygroscopic tension. Remember, we're allowing gravity to drop the water out if it can't be held by hygroscopic. And hygroscopic is the concept, if you have a little bit of water on a counter and you put a paper towel in it and you just barely touch the paper towel and the water scoots up the paper towel, that's the hygroscopic. So it'll attract itself to some solids, but it'll only crawl up so far before it stops. And that has to do with the attachment that it has to the material plus the weight of itself that is being pushed, then being sucked down by gravity. So once you get into sand, even the wilting point also is very low. And the sand can be very, very dry and to be at its wilting point. On the converse, clay, you can have up to, volumetric water content. So this is a concept of percentage of water in the soil. So not total. This is assuming that there's still at field capacity. That means there's another percentage of stuff up here that's going to be air pores. But just for the discussion, this has got about 37 or 38% of the water of the soil is water at both a clay loam and a clay. But if you look at the wilting point, well, the wilting point of clay actually is much higher. And that's because the clays is smaller and smaller particles, and therefore the pores in between those particles are that much smaller, and consequently the hygroscopic tension to hold water in those pores is sufficient that those pores don't drain. That's why we think of soils as being heavy, like a clay is a heavy clay, and we think sand is light. And it has to do with how we shovel them when they're wet. So even a moderately dry, or a clay that's at field capacity, or at wilting point, will still have 22-23% water in it. Whereas a sand at wilting point will only have 2 or 3% water in it.
I have a question for you.
Yeah.
Can you manipulate the water holding capacity of a sandy soil by adding humic acid solutions?
Not usually by adding humic acid. You can do it by adding organic matter. Because really, when you look at once to get a humic acid into a soluble form, the amount you're adding is relatively small in comparison to the amount of organic matter that is already there. So not usually with humic. The humics, we can talk about humics in a minute if you want to, but I'm not a great believer that humics really do that much other than activate microbiological systems. I know that there was a research report, and there's been a lot done on humic acids over the years, and it's been from the many early years of 1930s when we were trying to figure out what is soil. You know, there was the humic acids were uncovered as being having certain properties in the soil. However, adding humic acid alone in and of itself, I don't believe changes the water holding capacity. You have to add more dense concepts of organic matter and much more organic matter to get to the point where you can actually increase the soil moisture holding capacity of that soil. Yes?
Are you saying that the wilting point is higher because that water isn't available to the plants?
Yeah. Yeah. Think of it as being like a wine barrel full of basketballs versus a wine barrel full of BBs. You know, you have these huge spaces between the basketballs, and the only part of the basketball is going to be wet is just the outer periphery. That's the only part. Everything else is going to drain out the bottom. Whereas you have, or where the basketballs actually touch, that one area that's maybe the size of a dime. Whereas you get into a wine barrel full of BBs, they're touching all over everywhere. Some of the pores are small enough that there's going to be still a fair amount of water in those pores. So as you get smaller and smaller particles, you have smaller and smaller pores between the particles, and therefore those pores will still hold water even at the permanent wilting point. Let me show you the next one, because it kind of does it in the same. I'm going to go to this one. Let's see. I'm going to go to another one here. Let's go to this one. I'll go back. So this is the concept of kids getting a milkshake and a Coke, or you sitting at the cabana getting a drink with an umbrella in it. So this is the diameter of tubes down into a single fluid, like water. Well, if you try to drink a milkshake through a cocktail straw, you have to do an awful lot of sucking to get that thing up and through, and that's because of the friction and the tension that that milkshake has on the inside of that tube. That's why when you drink a milkshake, you want a big tube. If you go to a cocktail straw, which has water and alcohol in the fluid, it's very viscous, and so you don't really need a big straw. You can easily do it with the teeny-weeny little straw. So what this shows is that even if you have the same fluid, the water will actually creep up the inside of the straw based on the ability of that water to cling to the inside of that solid and cling to itself, because it essentially is, you know, only part of the water molecules are actually touching the surface. The rest of them are just touching each other, but it has to do with the way the water has what we call a dipole moment, because part of the soil water has a positive charge and part of the soil water has a slightly negative charge, and they reorient themselves so that the negatives are always next to the positives and the positives are always next to the negatives. And so, kind of like a chain, they can kind of hang on to each other. One sticks into the glass, the rest of them are sticking onto each other, but they can only hold that up for so long. If you have a lot of glass, surface area of the glass is more, you can have a lot more going up the straw. If the glass is wider, you're going to have not as many going up. In fact, if you measure the volumes in each one of these, I believe the volume will be more or less the same. It's just that the amount that water can go up. I think actually this one will have usually more surface area, so it'll actually go higher. But still, you can see the concept is the narrower the particle, the narrower the pore, the more water that pore can hold against gravity. Okay, let me go back those 4 slides that I skipped. Okay, we were there. Let me go to this one. Okay, so now plants actually feel water availability as the phenomenon of tension, at which the water clings to the soil particles, and the potential tension, or the suction. Keep in mind that pressure and tension are the same thing, it's just the opposites. One's pushing, one's pulling, and it's similar to like one person pushes a car, you have somebody in the front that's pulling the car, they both can move the car. It's just that one is using a different type of energy in relation to where it's moving the material. And in roots, what you do is you try to get them to suck the water out of the soil, and the suction is caused by the heat on the leaves and the evapotranspiration through the leaves, such that you get a contiguous stream of water going from the roots, wet, that have access to water, and the leaves are drying and have stomats that are open, and the water's leaving the leaves, and so people on top are going, hey, send up more water. You know, it's like, you know, Star Trek, hey, Scotty, give me more lithium crystals, we need more power. So there's supposed to be this continuous flow of water from the roots up into the vine so that it can do its things. Some of it is evapotranspiration and keeping the plant from getting too hot. The plant's tension is generated by the suction created from the evapotranspiration from the leaves. The tension is the opposite of pressure, and we can measure these things as the water content of soils in units of negative pressure. So tension is negative pressure, and negative pressure is tension. So we typically measure this in bars or in joules. I know if you go metric, we're going to stick to the English side of using bars. And this is similar to many of you that maybe use pressure bombs to help you with irrigation, where you go out and measure the stress in a petiole. Well, the petiole's up near the top of that chain of sending the water up. So frequently, those numbers will be higher than water tension 4 feet down from where that petiole is in the soil. But it's still the same concept. You can measure the soil tension just as much as you can measure the tension of the water and the stress in the vine to pull more water up from the soil. So a moist soil or a wet saturated soil is zero tension. It's got essentially no suction pulling on it. It's completely full. If you go to a flooded soil, then you have the weight of the soil on top, the weight of the water on top of the soil, and so you actually have a positive pressure pushing down on that water that's already in the soil. As you go to drying out a soil, we frequently, the bar system, even with our pressure bomb readings for petioles, the actual value is a negative bar, but we don't ever put the negative in front. We just say, oh, it's 12 bars or 14 bars, it's time to irrigate. Sometimes you get people that say negative bars, and everybody knows that we're always dealing on the negative side, because unless we're dealing with flooded soils, we're not on the positive side. But officially, it's supposed to be the negative side. So we know that as we go in this direction, we're getting from moist to dry to very dry. This is the kind of thing that the roots feel, because they're feeling only tension, the ability to get that water out of the pore where it's being held by the surface area of the material, the soil particle, and it's sticking to it due to a very light electrostatic bond. Similar to, like I said, either sticking to a paper towel or the same. It's very similar to rubbing a balloon on your head and sticking it on the ceiling. You just get a little bit of a charge difference between the two, and they'll stick. So what you need to do is just overcome that pressure or that electrical attraction to get these things to separate and move them up the plant. Okay, so when a contiguous stream can water in a contiguous stream can have different pressure potentials from the bottom all the way to the top. And so you can have like -3 bars. Usually we consider -3 bars to be, negative 0.3 is usually considered field capacity. So remember, 0 is saturated. Negative 0.3 is negative negative 15 is permanent wilting point. So usually negative 0.3, it's not field capacity, it's dry, but it's somewhat dry. If you picked it up and ran your fingers through it, you go, oh, it's still moist. There's still moisture in here, I can feel it. Okay, this is caused by the gravity, surface tension, friction, and evapotranspiration. So all of these things are causing a gradient from being relatively low, only negative 3, which if you go, I hate to do this, but if you go back, I probably ought to, it's a problem of dealing with low and high, because one's negative and one's positive. And so, we're on that bottom one that I just showed you, we're right here, a -3. So we're going to go now back to here, and as you get more and more up the plant, you can get, somewhere down here you might have -8, -10, and -15. Air is usually about a -500. So when you're doing petioles, that's why they always say, oh, you should do the petiole from the same position on the vine, because there's not only the tension of sticking to the surface, you also have gravity. So the water at the higher end has got more potential energy in it to go down because it's further away from the original source. You also have the surface tension and the friction, just the friction in the tube. So you've got a bunch of things going on. But typically, when we measure petioles, usually in the summer, you're supposed to pull the petiole from mid-cane. Usually it's they call it the 8th leaf or 6th leaf or somewhere around in there. And you need to be somewhat consistent because you're pulling out basal leaves on one vine and then the top leaf on another. Even if the plants have more or less the same water status, they'll give you 2 different readings. Okay, now let's go to 2 ways of measuring this. We have this soil moisture and the percent volumetric content, okay? We've already talked about that on some of the other graphs. That's just percentage of moisture in the soil. But we know from looking at that graph showing the textures that depending on the texture, the field capacity or the percentage of the available water in there is going to change quite a bit from sand, which was like we said 8% when it's at field capacity, 2% when it's at permanent wilting point, versus a clay that's 38 or 39% at field capacity and 20 or 22 at permanent wilting point. So we know they change over the textural class. So it's hard to know to compare these like apples to apples kind of concept. If you're measuring this from using a certain kind of meter, and there's some meters that measure this concept, and there's certain meters, soil meters, that measure this concept, and if you're using this method and you have two different textures, like you have a sandy soil and a clay loam soil, you can't compare the values of the two because they don't correspond to the demands of the plant on that concept of suction. So what we do instead is we use the negative bar, the bar concept, because that's really what they feel, is how much tension it takes to suck that next level of water out. It's kind of like us with a dish rag or a washcloth, and when it's wet, when it's really wet, it's easy to wring a little bit of water out of it. Every time we want to get more water out of it, we have to give it more pressure, to the point where sometimes we're wrapping it in a spiral and then twisting it and all this kind of stuff just to get that last drop out. Well, that's the amount of force that's required to get that last drop. Well, plants feel the same thing. How much suction do they have to exert on those roots to get that next drop of water out of the soil? And that's why in the summer when we get these high leaf water potentials, they'll be up at 10, 12, 15, and the drier and the hotter it gets, they go even higher because they're evaporating water, they have a demand, and the demand isn't being met in the soil because it just can't pull that next drop of water out of the soil. So it's better to be able to develop a concept of the soil moisture potential as being in a bar concept of tension rather than just on the percentage of water that's in that particular soil. Because this graph here shows, okay, here's your field capacity. Like I said, field capacity is usually about 1/10 of a bar, and permanent wilting point's usually somewhere around a negative 15 bars. And here's the graph in between, but you can see that this is this will change. This is for one kind of soil, like say that maybe like a silt loam or something like that. Whereas if we had a sandy loam, this whole concept would be different. This would be the same, but all of this would be different. So you need to be able to be at least somewhat conversant or at least knowledgeable that this is the way the vine actually feels the water that it's trying to pull into itself from the soil. Okay, this one's too busy, and I'm sorry. I hope the color comes out. So essentially, let's look at the green, which is the loam. So here is a negative 0.1. So this is field capacity. This purple line going straight up is field capacity for everything. The loam, it touches over, the loam is this black line, and it touches the crossover, the field capacity at this point right here. So it's about 35% of percentage of water in the soil when it's at field capacity. And go back down here to the negative 15 bars. This is the permanent wilting point, and it hits the loam hits the permanent wilting point at this point, which has come over here, and it's about 0.09% or 9% water. So the difference in between this green line and this green line, again, is that concept of available water between the two. The brown is the clay, and the blue, you can see the blue is the sand. Right here is sand at field capacity. Here's the sand at permanent wilting point, and therefore you can see there's a lot less water in a sand, even when it's really wet and allowed to just drain, than there is in clay. And the largest gap on this whole graph is between here and here. It's larger even between here and here, or they're about the same. Close, but they're about the same. But you can see that definitely the sand is a lot lower water holding capacity. I've already done that. I don't know why I put it in there two times, but it kind of reinforces this concept of how much available water there is related to the various textural classes. I already talked about this. Here's the basketball concept. When you have coarse sand versus fine sand, the fine sand's going to have a lot more contact points and therefore hold more water than the coarse sand. But you could just as easily change this to fine sand and this one to clay. I mean, it's just two different sizes classes. The smaller the size class, the smaller the pore sizes between the pieces that are in there, and therefore the greater ability to hold water against gravity. Here's another way of looking at it, where you have the available water and its pore is directly related to the pore size, where here's the pressure, right here's field capacity, here's permanent wilting point, and here is the diameter of the pore that's emptied at that level. And you can see that up here, when you get essentially at almost near saturation, you can have up to whatever, that's a pretty large pore, whereas down here you're having, 300 times smaller the pore is before you can pull the water out at this particular pressure. So again, it just goes into, the water that's in the biggest pores is easy to pull out. The water that's in the smallest pores is hardest to pull out. I've had this in here several times and it's confusing. I'm going to skip it. Okay, so now let's get into the concept of water movement as we work our way into the concept of irrigation, where you're actually adding water to the soil. If you have a soil that's relatively dry, or the whole concept of how water moves through the soil is what's called the hydraulic conductivity. Hydraulic obviously is water. Conductivity is how easy it is to move. It's almost its velocity. If you have a really dry soil, you only have the water film is just sticking to the sides of the particles. So typically to go from a wet area, which this area, you can see the thickness on this particle is thicker than it is down here, so the water will slowly flow this way. But it all has all this friction against the sides of the particles. Remember, because it's sticking by this electrostatic attraction. So you have a little bit of friction, so this water isn't moving too fast. When you get dry soils, water doesn't move from somewhat dry place to a really dry place very rapidly because the highway's too small. It's just a really small conduit from which it can go through, and it's got one whole side that it's sticking to that has electrostatic charge, so that slows it down. That's the friction. If you have water then all of a sudden you've got this water coursing in there. It's like a paving machine right in front of you driving 60 miles an hour, laying down all this new concrete. So all this water behind you just flows right in on top of this dry soil, and therefore when you water a soil, you know that it goes, especially if it's dry, it goes in pretty easily. It's easily soaked up. The percolation rate or the infiltration rate is relatively high. You can add a lot of water and it'll move pretty quickly. So a dry soil being wetted will wet pretty readily. A dry soil that you're just trying to move water from one location, dry location, to another really dry location is slow. And some of that's intuitively obvious. Okay, now, except at the very entry point, water does not move in a saturated front. And many of us, I think, believe that when you put that committer on there, you're going to get that water just going in. It's going to wet the soil in a saturated front, meaning that it's going to push all of the air out, and that soil, there's going to be no air in that layer as you slowly drip it on. And sometimes we believe this because if we look at underneath the emitter, sometimes you'll see it'll pond a little bit. Well, the reason it ponds is because when you drip the water onto these aggregates, the aggregates break apart. And then the clay separates from each other, and it plugs up the pores right underneath that surface divot where you're dripping the water. So it reduces the infiltration rate locally. But keep in mind that when you're dripping water into a pore or into the soil, you've got maybe a 4 or 5 inch diameter wetting zone, and that water can go in any direction. So it can go in 360 degrees in this way, any direction it can go, including not just, this is a flat screen, it can come out at it in both forward and backwards. So actually, once you get past the first maybe 1/4 inch or 1/2 inch of the soil being wet, from then on, it's not wetting by saturated flow. It's just wetting by going this, the superhighway concept, this one, where this is not completely saturated because you still have an air gap in there. But it is filling in, making the water film thicker around the soil particles, but it's not saturated. It won't saturate until you start putting enough water on. It'll usually saturate from the bottom up, where you get an impermeable layer below the water slowly gets down there at field capacity. It will slow down at field capacity. And then you'll get a saturated layer that starts to back up underneath. Usually it's a clay layer or a rock layer. And so when sometimes you hear the weather report people in the middle of winter, not these last couple of winters, but when we do have rain, and they'll say, oh, the soils are saturated. Well, sometimes they are. A lot of times they aren't really saturated, but they're at field capacity, but it doesn't take very much rain to get them saturated. And when they're saturated, they have a tendency to behave more like a fluid. They lose their strength, essentially what it boils down to. So they behave like a fluid, and then you start getting landslides or whole areas of hills that just kind of slowly or sometimes rapidly just slide down a hill. But usually we only have saturated situations for relatively short periods of time, because even if this is a clay layer, and if that clay layer is at all sloping, even 2 feet down, it'll slowly flow subsurface down to a lower layer, because gravity will push it down, essentially downhill. Even if that hill is defined by the slope of the clay layer, even if the soil itself is flat, if the clay layer below is sloping, the water will still flow down that clay layer until try to get to a lower point, and that situation is driven by gravity. Okay, so when we start adding water to a soil, if we're adding it to a sand, we'll frequently get the water leaving a pattern that looks kind of like this, where because there's not a lot of hydroscopic tension or a lot of contact, because remember we're talking basketball to basketball instead of BB to BB, you get the soil, you add the water, and the water just runs around each large particle or each large basketball as it works its way down. If you're dealing with something much finer, all of that surface tension will dissipate that water as it moves somewhat down but also out. And many times the surface tension becomes greater than the gravitational force, such that you get this kind of thing. You almost get a sphere. The wetting spot will actually be more round. There'll be a shoulder up here. Sometimes there'll be little shoulders down here. It'll look frequently more like this, but not like this. So this is like a clay loam or something like that. This is a sandy loam or a loamy sand. Now the important point here is that even after 24 or 48 hours, and you've added, let's say you've added a gallon of water, this is where that gallon of water is after 1 hour. Over here, this is where the gallon of water is after 1 hour. But if you let it sit and you don't let it evapotranspirate, then after 24 hours, you can see that this is much broader than this one. And if you let it sit another 48 hours, and this one doesn't have the 48, but you can see that it's dissipated over a much greater distance or more volume of soil. Even though it's still 1 gallon of water, it's dissipated over more volume, and consequently, it's spread thinner, meaning that the film is thinner, meaning that it's going to take more energy to get it out again. Let me go to the next one. Up. Next one is really. I'm going to come back to this slide in a minute. Actually, it's further into the presentation. This next one is another one that's really kind of confusing, and I'll explain it, but it may be a little bit difficult to comprehend. Okay, so this is the actual evapotranspiration rate, and I'm trying to put a concept here of the evapotranspiration potential, like how much hot weather is there out there that could actually start pulling all that water up from the roots up through the vine, which is the potential. How much soil water potential there is, and really how much water there actually is in the soil to be pulled upon. And then based on these two things, we actually get the actual evapotranspiration rate. So we know that in the winter and the summer, on a hot day, and we haven't watered for a while, we have a high amount of water evapotranspiration potential. We don't have very much water in the soil, therefore we're not going to have very much water coming up and out. And that's looking at it down here, this thing, where we have the evapotranspiration potential is, is high. Let's say the evapotranspiration potential is high, but the soil water potential, it's negative, is very low. This is down near wilting point. So that is, you're not really going to get a whole lot of water out of that situation when you even have a high potential, but you don't have much water. You're not going to pull much water out. You're most certainly not going to pull much water out if you have a very low evaporation potential and the soil is still dry. So let's say we're into October, still no rain, but our days are only getting up to 62 or 63, so it's not really hot. That's this whole graph, where it's not really very hot, so we don't have a lot of potential to draw out water, but we also haven't irrigated, so we don't have a lot of water there. Therefore, our actual evapotranspiration is very low. On the other side, when we do irrigate in the middle of July, we have a situation where we have our evapotranspirational potential is high, so it's up here. Our soil water potential is it's negative number, so we're trying to get it back up to field capacity, and therefore we're at this point right here. So when we have high potential, high amount of water, we actually get high actual evaporation. So when you are thinking about berry sizing after berry set, and you're going, well, do I really want the vines to have access to an awful lot of water in a short minute of time? Because they'll gulp it up. Let me go to the next one. This is the beginning of several slides that are going to look at an experiment in which the viticulturalist grew, I think this was Cab. It might have been Merlot. I can't remember. But at any rate, they grew it at 3 different soil moisture potentials. So they tried to keep the soil moisture potential constant in each soil throughout the season. And they chose 80% of available water, so it's a little bit less than field capacity, 30% of available water, so it was a lot below field capacity, and 15% of available water, which means it was getting close to a permanent wilting point. And this graph is just the initial graph, just shows how good they were at maintaining the water over time. Here is the day, from WS, who can read really quickly here, it was WS, I think it was berry set or something like that. WS, water stress start. Okay, this is where they started the water stress, because otherwise they were all kept at the same level of 80% available water. And then they started to let this one dry out, and you can see they kept that one pretty dry. At the end they added a little bit of water, but pumped up a little bit over the 30%. Oh, wait a minute, that one is 30%. So the 30% got a little bit too dry. The 15% got down to 15, stayed there, flat-lined, and was relatively good. This one, they started the watering a little bit late and did get it back up to 80% of available water, but you can see it also went through somewhat of a dry stress where it got down to about 50%. So they weren't perfect in monitoring or supplying the water, but just to let you see what they were trying to do. Do you understand the concept here? They're following their water regime over time? Okay. Okay, so here's their sap flow. So they were measuring essentially sap flow up through the trunk. I don't know if you had a Fruition Science come down and talk to you all about sap flow meters. Okay. So this is a similar type of instrument where it's measuring sap flow, and you can see that the ones that are at 80% of available water, you give them the water and hours of day, and right around 2 or 3 o'clock, which is the highest evapotranspiration potential, they're sucking up a lot of water. If they have the water, they're going to use it. Whereas those that are at 50% are pulling up less, and those at 15% are pulling up a lot less. And as you go through the year, August 14, 24, the 25th through the 3rd of September, you can see that the temperatures were getting cooler, therefore the evapotranspiration potential was a little bit lower. So they didn't have to use as much water, but the same thing kept holding out over time, is that at the hottest part of the day, the one that was at 80% was allowing the vines to use essentially as much water as they wanted to bring up, and the ones that the lower water holding capacities just didn't have enough water, and it would have preferred, the vine would probably preferred to be up in this range rather than stuck down in this range where it just doesn't have as much water as it needs. And then they go through the season. Here we are at October, starts to level out just because we just hadn't have as much evapotranspirational potential, and it was getting cold. Even the days were cool enough that we just didn't have the high potential. But even still, the pattern is the same, where we had the one that was the water usage was still highest among the one that had the most available water. Okay, let's look at this in relation to the date and the leaf water potentials. I think this is leaf water. Yeah, pre-dawn leaf water potential. So no evapotranspiration really occurring. It's pre-dawn. It's before the sun comes up. So it's, for you all around here, it's probably, 50, 48, 59. I don't know what temperatures you get in the morning here in the middle of July or whatever, before the sun comes up. But I assume it's down in the 50s like almost all the coastal ranges are. You can see that even the pre-dawn leaf water potentials, the 80% had plenty of water. The 30% had, or the 30% had a fair amount of water, and the 15% just didn't really have nearly as much, and it was a lot more negative. It would probably have preferred to have more, but it was much lower in the availability of essentially the leaf water potential, or the pressure bomb readings, were much more negative. And to change these from megapascals, just move the decimal place over 1 to get to bars. So this is 10 bars, 12 bars, 14 bars. So by the time you're getting to the middle of September, which frequently will have heat spikes, that kind of Labor Day thing that comes through. We're still pretty warm in September. They were still having, having trouble with maintaining leaf water potentials of even less than 14 at 6 o'clock in the morning. Here's the berry diameter, and this is part of the take-home message for those of you that believe that you want smaller berries. Here's the berry size in diameter under the different water regimes. So you can see that if you're giving the vines a lot of water, you're going to get bigger berries. If you give them less water, you're going to get smaller berries. And it's, again, most of us have figured that one out also just by trial and error, and the winemaker yelling at us to get the berries smaller. So what are the implications of some of this is that if we reduce the vine's exposure time or the frequency of irrigation, not the duration of irrigation, but the frequency, how frequently you actually turn on the water. If you can reduce the vine exposure time to high water potential to encourage smaller berries. So you let them dry out more and more and more before you turn that next gulp of water on. If you're shallow watering where you don't give them as much, you're going to have to water more frequently. And remember that during that period of watering, or the day or two after watering, they're going to be in the big gulp situation. They have access to a lot of water because you just added it, and they're going to be using that quickly, and then they're going to stretch it out. They're not like us when we look in the refrigerator and we don't have any money in our pocket. We have to go another 2 weeks where we start eating, slowing down, or, going into the cupboard and finding a little bit, food in the back pantry that we normally wouldn't eat. And these guys are going through like a hungry dog. They're going to eat as much as they can and get as much of that free water as they feel like they can until Mother Nature forces them to slow down by not providing enough water to meet their demands. So to reduce vine exposure to high water potential, actual time during irrigation, which is the actual time during irrigation, during periods of highest water demand to allow water to be dispersed over more soil volume and lower water potentials is to irrigate when the ET is low. So remember that, let me go to this one, I think it's this one, right? There we go. So going back to this diagram, if you add a gallon and you water at, say, 11 o'clock in the afternoon, and you add a gallon, when the demand is high, it's going to use a lot of that water. If you water it at 6 o'clock at night or 8 o'clock at night, when the demand is not that high, because you have lower evapotranspiration potential, because the temperatures are so much lower, you're going to allow that water to dissipate out into a bigger wetting zone. And it's the same gallon. It's just spread over more volume so that the next morning when that vine wakes up and starts to pull on water, it doesn't have the easy water. It's got all the gallon that you added, but it's much more difficult to pull out that initial day or two. It doesn't have the really, really easy stuff. It's going to have to pull it out still over a 1 or 2 week period, or maybe not a gallon over a 1 or 2 week period, but if you've done it with 3 gallons or 4 gallons. But it's not going to use a lot of it right that first day and then slowly go into the starvation point. It's going to be somewhat under stress from the beginning of coming out and having higher evapotranspirational demand, 12 or 15 hours, 10 hours after. Well, it would be, from, let's say you watered at 6 o'clock at night, by the time the sun comes up and starts putting an evaporational demand on it at maybe 9 or 10 o'clock. So, you're looking at what, 14, 15, 16 hours. You're just going to allow that water to dissipate over a much greater area so that you don't have as much easy water for that vine to take up. And we know that if you don't have easy water for the vine to take up, you're going to be in the smaller berry size. Now, obviously, this was done seasonally throughout the entire season, but essentially that's to some degree how they did it. And that is using irrigation at certain times of the day or maintaining the soil moisture at a certain level so that they didn't have this luxury consumption or massive consumption of the water that you've just added. So watering at night or late in the afternoon will reduce application rates or frequency, thereby irrigation costs, energy and water, will reduce the berry size and hopefully improve quality. So unfortunately, most of us work, if you're a vineyard operator, you're working, your guys will start showing up at 6 o'clock in the morning and everybody's gone by 3:30 or 4. So unless you have an irrigator that's willing to be a night owl where he's out there turning valves on and off from 6 o'clock at night until midnight in the dark, it seems to be somewhat unreasonable to do it this way. But it will save you in water, energy, and it'll end up giving you a smaller berry size, which many of the winemakers, I know it's to some degree, it's not been disproved, it's just been shown it's not as influential necessarily as some people think it is, but you still will end up with a smaller berry, which means you'll have a slightly higher skin to pulp ratio for your, especially for your red wines where most of the flavor components are in the skins anyway. Okay, now we got that. Let's go into a little bit more on how this comes about in relation to how we water stuff. Okay, we all have this intuitively obvious, I hate to use that frame, but it's, at this point in your farming career it probably is, and that is, if you have a soil with not a lot of rock in it, it's not going to hold as much water. And if you have a soil with 75% rock in it, it's going to hold, if you have a soil with no rock in it or very little, it's going to hold a lot. If you have a soil that has 75% rock, it's going to hold a lot less water because the rock itself doesn't absorb water. It's only the soil that absorbs the water. So, managing variation on soil properties, proactive, have a professional soil scientist evaluate the properties and the variations in your soil to design the vineyard based on compartmentalization of soils of similar soil properties, especially water holding capacity. Water holding capacity is I think it's the major component of vigor, more so than nitrogen. Although nitrogen is important, we can easily regulate nitrogen because if we don't add it, nature doesn't provide a whole lot of it for free. Small amounts through organic matter, but not a lot for free. So as long as you're not adding a lot of organic matter, the easiest way to moderate vine vigor is through water. So what you want to do is when you design a vineyard is to design it so that you have compartmentalization of similar soils in the same block. And if a soil changes from one water holding capacity to another water holding capacity, then you want to draw a block boundary. You don't necessarily need an avenue, but you want to put it on a different irrigation system because you're going to need to treat it differently. Otherwise, you're going to end up with a really highly vigor one end of a block, and then the other end is going to be low vigor. And when the winemaker walks through there, he's going to say, okay, we're going to have to pick this in 3 different days. We're going to pick the one end first, then this next end, and this other end is still green, and we're not going to pick that for another 10 days. And it just makes your harvest situation a lot less efficient in the attempts by the winemaker of getting more uniform fruit and more high-quality fruit into the winery. So compartmentalization of your similar soils in the same block and separation of dissimilar soils into separate blocks is one of the goals of designing a vineyard. So the post-planting, if you have the managing the variation, is you can manage the variation in the rooting depth, because sometimes we do have different rooting depths. We normally think of trying to rip a soil within a block to being the same depth, but over time, you may find that roots in rockier soils don't go as deep, and there are methods of actually increasing the rooting depth of a soil that's still already planted to a vineyard, and then manage variation in water holding capacity. So there's several ways of doing this. Okay, so just an example. It's kind of a little difficult to see with the light shining on it, but this is a soil with loam, light clay, medium clay, sandy clay. So it's a heavy clay soil with essentially, or moderately clay soil with very little rock in it. It's got 5%, 10%, 10%, 10%. It's got granular structure, and then it goes into this clay that's massive. The stuff underneath it is massive, so it's not, you still essentially have a rooting depth in the track layer of many roots. The effective rooting depth is only about 20 inches here before it hits that clay layer, and then the clay layer stopping the rooting. When you compare that to something like this, which again is kind of hard to see, but you have sandy loam, loamy sand, which is almost like beach sand, and then loamy sand underneath it that goes from 5% rock to 30% rock to 80% rock. And this is the kind of pit that you get into, and actually the bottom caves in. The loam has enough cohesion to kind of hang in there, but as soon as the backhoe gets digging it out, the bottom is so loosely fitted together because it's just loamy sand and gravel that it actually fills into the hole underneath, and it gouges out the soil underneath underneath part of the pit. So, and this one is obviously going to have a very different water holding capacity than the soil we just previously saw, primarily because this is, when you look at, although there are fewer roots, when you look at the hardness of this soil, friable, loose, I mean, it's surprising there weren't a lot of roots in there. And actually, this soil was not in a vineyard at the time we were looking at it. So that's why the roots haven't gone deeper. But in designing the vineyard, I wouldn't want to put these two soils in the same block because I'm going to have trouble controlling rooting depth here. Whereas on the first one, I have a clay layer that will control rooting depth. So definitely, there's going to be a line between the two. I'm going to put them in two different blocks. They're going to want to be irrigated, or I'm going to want to irrigate them differently. Or something like this. This is probably closer to what you all have. Well, not fractured rhyolite, but where, and this is what I've seen in my other experience up in this neck of the woods, is that you get, you know, a lot of rock right up near the surface. It's not alluvial rock. It's fractured sandstones, fractured shales, and therefore the water holding capacity is very low. You have, you know, 95% slightly fractured. This one's rhyolite, which is a volcanic ash, or 100% slightly fractured rhyolite. And even here, you have 80% fractured angular rhyolite. So your water holding capacity here is almost nil. So here, unfortunately, you're going to be watering relatively frequently. But you can see there's rather profuse rooting, at least down to, you know, the 17 and actually even into this slightly fractured sandy loam. Okay, so when it comes down to the irrigation and planning your irrigation, you really need to know your root zone. It's nice to have a soil scientist do it because that's what I do for a living. I love to go out and dig holes in vineyards and get paid for it. But this kind of thing that you can probably do on your own if you have either a mini excavator that can get down the rows that you have, or somebody that's willing to dig a shovel into rock, which is a lot harder. But it does behoove you to go out and know what your root zone looks like. And one pit isn't enough. You'll have to go do 3 or 4 or 5 and just get a good feel for, as you move across a block or across your vineyard, you know, what does it look like? How deep are these soils? When do I start hitting rock? When do I start hitting high concentrations of rock? What are the textures? So you know more or less that the concepts of how much water the various textures will hold, and you can subtract off the rock content. So if it's 50% rock, you know you only have 50% soil. Therefore, even a clay loam is going to be holding 50% less water than a clay loam that didn't have any rock. So seeing that, and also doing it, it's best to do it after you irrigate. Go ahead and give it whatever your normal irrigation is. Within a day, go in and dig the hole, because that way you can still visually see the wetting zone. And you can see whether you're wetting your root zone, whether you're wetting below the root zone, which means you're wasting water, or watering way too shallow, and you could be putting on more water, which would decrease the frequency at which you have to water, and therefore you're not giving them that 24 hours of gluttonous uptake of water. This concept here, this is just a schematic of looking at the total available water in inches of how much water is actually in the soils. Like most soils are like a loam will hold about 1.5 inches of water, of available water per foot of soil depth. So here we have a soil that's about 18 inches deep, and it's got an undulating upper subsoil of about 30% rock, and then it's got a lower subsoil of 95% undulating rock. And so this is the kind of thing that it's not completely, the scale this way is not the same as scale as this way, but you can see that if you have the total available water here down to 36 inches is 3.8 inches, whereas the total available water over here is only about 3 inches. So it's quite a bit less water at this location than here, primarily because you just have so much rock in this particular one compared to over here. And so in designing a vineyard, this is the kind of thing where I'd go, well, I don't really want to have one vine that's growing in this situation where it's got all this rock, because it's not going to have nearly as much water as over here. So this is one where you'd either rip it to maybe 24 or possibly 30 inches, but you wouldn't want to rip it any deeper than that, because as you rip it deeper, you're increasing the variability in the rock content and therefore in the water holding capacity, and therefore you're having the one wet part of the vineyard and another dry part of the vineyard. So it'd be better to separate the irrigations, put them on 2 different ones, and treat them differently because they're different. The other issue we frequently have is in rocky soils especially, you hit rock at a relatively shallow depth. You end up having, if you dig a hole, you'll find most of the roots are under the emitter. They don't go out here and proliferate where there's not a whole lot of water. Yes?
Where does sandstone fit into your rock?
Sandstone is slightly porous. So when I do these things, I have a model that kind of gives me a calculation of how much water holding capacity there is with depth. And usually I consider sandstone to be, it'll have an available water holding capacity of approximately 2%. Whereas like the rhyolites or andesites, basalts, they usually are zero. They don't suck up any water, they don't give off any water. At least the sandstones, and to a lesser degree the shales, will store a small amount of water that it'll give back, but it's small enough that if you ignore it, you're probably still pretty safe. So you're not going to get a lot of water storage actually in the sandstone. If it's 30% sandstone, you're still getting the water storage in the 70% soil, but you can still get the penetration, yeah, but you're not necessarily getting that much more water holding capacity. Okay, so here we have essentially an asymmetrical root zone and shallow. So the option is to go ahead and put in another emitter so that you can then get two root zones. So instead of having an architectural root zone that is vertical, you go, look, we're not getting any vertical out of these soils because there's so much rock underneath it, there's not any place for it to go. Let's go horizontal. You still increase the amount of soil that can absorb and hold that water for you, and that way you can fill this, and you only have to put on the irrigation for an hour to get your 2 gallons instead of for 2 hours to put under just one emitter, where most of it's going to be, or half of it's going to be lost into the rock below. So you can do double emitters. You can also come in and put in double poly, where you punch in emitters. Here's where if you continue with the amount of water that you were putting in, you're wasting, and if you put in another emitter, you'll just waste the same amount on the other side. Or you can put in a smaller emitter, double poly, with a smaller emitter on that one side to better match what you're trying to accomplish. I'm going to skip that. The other method is to increase the root zone. You can do this with, this one is owned by John Crossland down in Paso Robles. At this point, there's several of them. I know Napa and Sonoma, we have several vineyard management companies that have bought these. They're in-row rippers. They have a wing on it so that when they go through the soil, they lift the soil up a little bit. They will end up pruning the roots, so usually when you put these in, you have to use them in 2s because you want to get it relatively close to the roots so it's loosening the soil around the roots. But if you have only one, the tractor will rotate around it and bang into the vine. So you have to have 2 to keep it symmetrically going down the row. But you only want to do every other row because it will prune the roots on this side of this vine and on this side of this vine. And so you don't want to prune the roots on both sides of the vine in the same year. So you probably want to do it 1 year, mark which ones you did, and then come back a year or 2 later and do it on the row, the alternate row. But these usually can go down, depending on the power, usually you can get at least 18, sometimes 24 inches. So if you have if you get in and do soil pits and you find out that the original ripping before you planted has you have room where you could put, there's more rooting space before you start hitting really hard rock, but your roots are still, most of them are only at 12 or 14 inches deep, go ahead and come in with a 24-inch ripper. Or if most of them are at 24, but there's a lot of them still that are some of them are at 14, some are at 18, some are at 24, come in and rip it uniformly to 24. That way all of them can get down to 24 inches so that you increase the uniformity of the water holding capacity by increasing the root zone of the ones that were the shallowest, but you're not increasing the root zone of the ones that were the deepest because they were only at 24 and you're only ripping to 24. So what it does is it narrows that gap, the range of rooting depth to 24 and above instead of 14 to whatever it was. So it makes it more uniform in its water holding capacity. Okay, near the end here, summary, water moves in a non-saturated front. It's removed by roots from the largest pores first and then progressively smaller and smaller pores. The water is removed. As the water is removed, the water potential, which is the force required to remove the next increment of water, becomes more negative and more difficult to pull out. This impacts the leaf water potential up in the vine, and the leaf water potential is a direct indicator of the water stress the vine is feeling due to the availability of water in the soil. I think I went, yeah, 2. Methods to improve irrigation efficiency and fruit quality: know the depth of the root zone across a vineyard block, reduce the period the vines have access to easy water. Provide water at night so it's distributes to more negative soil water potentials prior to its next time of peak use. And water only when leaf water potentials indicate need and not on an arbitrary schedule of just every Thursday or something like that. I think that's it, yeah. Oh, no, wait a minute. That's summary number 3. Let me see what that is. Oh, reduce variation in the water availability by adding emitters for horizontal root architecture, adding a drip hose for weak vines, or an inter-row rip tillage to increase the rooting depth of the shallowest root zones. Any questions? Yeah.
Is there any
there's always cation exchange going on, because the cation exchange is the phenomenon of the cations that are soluble and in the soil solution, and their attraction to the broken edges and therefore negative charges of the soil particle. It's just that when you have less water, that water film is thinner, and therefore your concentration of cations is greater because it's not diluted as much. When you add water, it dilutes it dilutes the amount of water, you add water, it dilutes the concentration of the cations, but it doesn't change the cation exchange capacity. The same amount of cations is still there. Yeah. It's just not as compressed up against the soil particle in the thinner film. However, you do have a greater leaching potential to leach some of those cations out as you add water to an already expanded wetting thickness of the soil. So that's why you don't necessarily want to continually, when we put on fertilizer, if you're putting on nitrogen fertilizer, like a nitrate of some sort, that rapidly changes or stays negative, it's a negative charge. If you're going to do a 3-hour watering, you don't want to add that nitrogen fertilizer until near the end of it. You'll probably add it at the last hour, let it run for 20 minutes, and then let another 20 or 30 minutes wash it in. If you put it at the front end of your irrigation, something that's negatively charged, it doesn't stick to the soil anyway, it'll just be flushed through the root zone because you have all of this water with relatively thick water films around the particles repelling that negatively charged nitrate, and it'll just flush right straight through outside of your root zone. So there's some implications of the irrigation also in relation to what fertilizers you might be adding. With phosphorus, you probably want to put the phosphorus on at the beginning because it doesn't leach very well, and the more water you can get, the deeper you can get it to leach. With nitrates, you probably want to go the opposite direction. You want to put it on last, or nearly last, so that you keep it in the soil root zone. Any others? Oh, yeah. Yeah.
To preserve water retention?
Okay. The tillage, usually when you first plant a vineyard, I always recommend that you come in and do tillage of some sort. Even if sometimes you'll get in soils that are really sandy and they're really relatively loose in the surface horizon and not that hard even in the upper subsoil, but you want a uniform soil hardness when you put those vines in the ground, because even the hardness will undulate or change across the landscape. And by coming in and doing a tillage, it loosens it all up to more or less an equal amount. So it makes it uniform hardness, so that when you put the vines in, they're growing into a uniform hardness, which means the vines will grow more uniformly in comparison to each other, and consequently you'll get what's called an even stand. You won't have some really weak vines and some really strong vines in relation to ones that's deep, shallow rooted, because it didn't really penetrate that hard layer that you didn't till. So we want to till to get a uniform hardness. Once you get the vineyard established, that usually the hardness, the soil will recongeal to its natural hardness within a 3 to 5 year period. So within 5 years, most of the soil around your root zone is back to being as hard as it was naturally. And that's why in viticulture class, they always say, put all your effort in the first 3 years into getting a good root zone established. Don't worry about getting a lot of crop off of it. Cut the crop off the second year. Only take a little bit of crop the third year if you need it. That's because you want to get all the carbohydrates that vine is producing into root production before that soil starts to recongeal back to its natural hardness, so that you get it very well distributed in the soil. The next concept of till versus no-till frequently has to do with cover crop management. Personally, I like to see cover crops, especially on hills, and legally in Napa we have to have them where they're regulated. Depending on the slope, you have to have a certain amount of cover crop. On the flatlands, it's up to the individual. Obviously, cover crops take water, so many times we'll use the cover crop to help dry the soil out in the spring, and then we'll come in and either till it under or mow it into dormancy. As far as tilling to get better water infiltration, since most of our infiltration occurs in the winter, I can understand why people might want to come in and slightly or lightly disc a soil in the fall. if it's relatively flat, you know, not more than 5 or 10% slope. But if you come in and do a slight tillage and therefore kill or severely destroy your vegetative cover crop, when you do get these big rains like we got in December, where you get 9 or 10 inches in a 3 or 4 day period, you've really set yourself up for erosion. And you're eroding the most valuable soil you have, and that's the top, because that's the most nutritionally valuable soil is your topsoil. So unless you're planting a cover crop, you're only tilling it to loosen it up enough to get the cover crop seeds in. I would not do any kind of fall tillage, and the only other tillage that I would recommend is putting in tillage if you are trying to conserve moisture and it's after the rainy season has ended, and you know that your ability to, or weather to come in and erode your soil is greatly reduced, and you're doing it primarily just to preserve the moisture you have in the soil for your vines and not give it to the cover crop. Does that answer your question? Okay. Well, like I said, thank you very much for having me.
Thank you very much to Paul Anamosa. We've been waiting a long time for this presentation, and it was